Okay, well, thank you very much. The story is entirely true. So on the way out, it sort of gave up. So I downloaded this used version of the talk from the internet. And anyway, so I don't know anything about complex systems and very little about topology, and I didn't know what the audience is like, so I decided to give a very general talk. So I'm competing for the most elementary math talk given in this building in 2014, and you'll be the judge, okay? Particularly, I'll explain the picture. So let's start out, right? So all undergraduates learn about solving linear equations. So you might get this in your homework sheet as the input, and you're supposed to get there, right? So that's what you learn as an undergraduate. Now, linear algebra is absolutely central to scientific computing and applied mathematics, and numerical methods in linear algebra sort of, rule the world as far as applied topics go. But then there's also nonlinear algebra. So this topic is sort of about transitioning from linear to nonlinear algebra, and not all, but some undergraduates learn about Grobner bases, a general method for dealing with nonlinear algebraic equations. So for example, this might now be the input, and then you say solve or something, and out comes the Grobner basis. Now you notice something here, that the output on first glance looks more complicated than the input. Right? So that's certainly intimidating. But there's also good news, right? We still have the system in triangularized form. So there's a single equation in one variable of degree 12. You back substitute. There are two equations for y, solutions for y. And finally, you can express x. So we see that there are 24 complex solutions to this system. And that's a nonlinear algebra situation. Now, nonlinear algebra really is sort of the algebra of algebraic geometry. So in algebraic geometry, we study zero sets of polynomial equations, algebraic varieties, often in applications over the real numbers. And this is a picture of an algebraic variety, a Kummer surface, right? So to some people, this is almost a group. You can multiply 2 blue points and get another blue point. So here's what this talk is all about. So what I like to do is I like to give you 3 different tapas of applied algebraic geometry. The first third of the talk is about tensors and tensor decomposition. Tensors are a subject of multilinear algebra, and as such lies between linear and nonlinear algebra. Second topic, I like to tell you a little bit about sort of recent perspectives in polynomial optimization. And then finally, algebraic statistics. So I think that was kind of intended to tell you a little bit about algebraic statistics, and that's the third part of the talk. So that's the plan. And again, there will be various pictures that I'll explain along the way. This, by the way, was the cover picture of the notices 2 months ago, AMS notices. Okay, so let's start with tensors. So for me, a tensor is an n-dimensional array of numbers, x, I, j, k. So for n equals 1, such an array is called a vector. For n equals 2, don't smile, I'm competing for the most elementary talk. For n equals 2, this is a matrix. And then for n equals 3, we have these sort of 3-dimensional arrays. So for example, this is a picture of a 3 by 3 by 3 tensor. So imagine this being filled with scalars in a field. So this space of these tensors is a 27-dimensional vector space. Now a tensor has rank 1 if it's an outer product of vectors, right? So here's a take-home message. What's a rank 1 matrix? It looks like this, right? It's a column vector times a row vector. That's a rank 1 matrix. What's a rank 1 tensor? It looks like that. Okay, so there you go. So so that's a rank 1 tensor, and the textbook to read maybe is Landsberg's book on geometry and application and tensors. Okay, so those are the basic decomposable rank 1 tensors. Now, why would we care? Well, why would we care about tensors? Let me tell you why we care about matrices. So after truth and beauty comes statistics. So here's a little story I learned from an introductory textbook in statistics from the UK. So 296 subjects aged 40 to 50 were asked about their hair length and how many hours per week they watch football, also known as soccer, on television. Now these data got discretized, right? So we make ternary random variables. So the question is, does watching soccer make you lose hair, right? So every day in the newspaper you read that some food or some behavior causes some medical condition. So we'd like to study this question. So let's discretize, right? So you self-classify either to have, you have a lot of hair, medium amount of hair, or you're close to bald, very little hair, right? And this is how many hours you watch per week soccer, very little, medium, a lot. Like the real fanatics, they watch all the time. And then, you know, so there are 29 people with very little hair and medium amount of soccer. So a question you might ask, is there a correlation? Before we get to causation, let's talk about correlation. So is there a correlation between watching soccer and losing your hair? Okay. Well, suppose these two things were independent. What would that mean for our matrix? Well, that would mean that's a rank 1 matrix. Right? So independence is rank 1. The probability of having a soccer state I and hair state J is the product of the respective probabilities. So for perfect independence, we would have a rank 1 matrix. Remember? Rank 1. So now, if you look at this matrix, the 2 by 2 minors are not 0. In fact, it was rigged up that they're all quite positive. So the 2 by 2 minors of this matrix are rather positive. So this suggests that there might be some positive correlation. Right? That positive correlation between lots of soccer and little hair. So let's, well, the answer is not really, right? So there's a mysterious hidden random variable called gender. Gender is a random variable that has two states, male and female. And suppose we knew that our data were the sum of a male table and a female table, right? And again, this is set up so that the male table is rank 1 exactly, and the female table is rank 1 exactly. Then we have this as an example for the concept of conditional independence. Right? So I have two tables of rank 1. The sum has rank 2, that's the definition of rank. And so here, this is a textbook example for the concept of conditional independence. Now maybe sort of one line of actual statistics on statistical hypothesis testing. You would formulate a null hypothesis. So the null hypothesis that these two variables, soccer watching and hair growth, are independent given gender. Right? That's the model, the conditional independence model. And this table very much supports this. Now, statisticians are fussy people. They never, ever, ever accept the null hypothesis. They either reject or they don't. So based on this data, we'll do a little p-value, and we're led to conclude that we don't reject the null hypothesis. So this is why we're interested in tables. And notice that this decomposition is into non-negative rank 1 tensors. OK, so a couple definitions. So in tensor decomposition, we would like to decompose a tensor as a sum of rank 1 tensors, just like in the matrix case. And we like to use as few summands as possible. So we'd like to have the hidden explanation to be as simple as possible. And we're going to say a tensor has rank R if it is the sum of R tensors of rank 1, not fewer. So, as in this cartoon. Now, over the real numbers, or any ordered field for that matter, there's a notion of non-negative rank. Right? So, a non-negative tensor, such as my soccer data, has non-negative rank R if it is the sum of R non-negative tensors of rank 1. Okay, so the non-negative rank is greater or equal to the rank. But we'll see they may not be equal. Now, what's math? Well, poetry, it has been said, is the art of giving different names to the same thing. Mathematics, on the other hand, is the art of giving the same name to different things. So here are a bunch of things that look very, very different on the face of it. So for example, the set of tensors of bounded rank, 4 by 4 by 4 tensors of rank at most 4. I like the number 4 because that's the cardinality of the set ACGT, the nucleotides. Here is the parametric representation, then the mixture model for independent random variables, the naive Bayes model, the conditional independence model. In geometry, the fourth secant variety of the Segre variety. the general Markov model in phylogenetics, and then various formulations in physics. So all of these things are the same. So in mathematics, we give the same name to seemingly different things. Now, Elizabeth Almond, who is a mathematical biologist, asked the question, what are the equations that characterize this set? Right? So for matrices, if we're interested in matrices of rank at most 4, we know that the minors of size 5 characterize this. So one way of characterizing low-ranked matrices, well hated by numerical analysts, is the vanishing of subdeterminants. So we can ask the question, what is the analog for tensors? Now, Elizabeth Almond is at Fairbanks at the University of Alaska. And as we all know, since Palin's candidacy, Alaskan women, they are pretty wild. They go out there, they go hunting and fishing, and her salmon problem came with the prize. So in her backyard, she will catch for you a salmon, gut it, smoke it, and ship it to you if you find the prime ideal in the polynomial ring in 64 unknowns that characterizes the set. Now this was, I think, the first batch of salmon was shipped out. So this was solved set theoretically in 2 papers by Friedland and Gross and Bates and Oeding. So the ideal theoretic, the scheme theoretic version is still open, but we know equations that cut out the set. But before we get to rank 4, let's get to rank 2. So 2 is the cardinality of the set pyrimidines and pyrimidines. So let's talk about the rank 2 tensors. So, and let me, before I state a theorem or 2 theorems, let me define the flattening of a tensor. So it's convenient to take the entries in a tensor and really write it on a sheet of paper. Right? It's sort of hard to carry a 4-dimensional cube around full of numbers. It's more convenient to write this on a sheet of paper, and we call that a flattening. So suppose you have a 2 by 3 by 5 by 7 tensor. So there are various ways to write this as a matrix. So for example, you could aggregate the first 2 indices and the last 2, and then write this out as a 6 by 35 matrix. But you could do it other ways, right? You could also write this as a 5 by 42 or 14 by 15 in the obvious ways. By aggregating dimensions, you can flatten a high-dimensional tensor and write it as a matrix. Now, under this operation, the rank can only go down. But sometimes it's exact. So here's a theorem proved set theoretically by Landsberg and Manivelle, and Raiku showed that the ideal is correct. So a tensor of any format, so of any dimension and any format whatsoever, has rank at most 2 if and only if all its matrix flattenings have rank at most 2. So the only if direction is easy, so the content of the statement is the if direction. So if somebody hands you a large high-dimensional tensor, then that tensor has rank at most 2 if and only if all the various matrices that you can get by writing it as a flattened tensor as a matrix have rank at most 2. Now, there's a little bit of fine print when you talk about tensor rank. Namely, the tensor rank A depends on the field. So over the real numbers, the rank is generally larger than over the complex numbers. Also, there's an issue of closure. So if you take a sequence of tensors of a given rank, in the limit, it can go up. Right? So these things cannot happen for matrices. So for matrices in undergraduate linear algebra, we learn that the rank can only go down. If you have a family of matrices, it cannot go up, and it doesn't matter what the field is. This is a feature. This is not a flaw. So it's really kind of a flaw that an ordinary linear algebra for matrices, it doesn't depend on the field. That's very, very special. In some sense, that's too special. So it's a feature of nonlinear algebra that we have to be a little bit careful about the field and about the closure. Now, there's a companion theorem with Allman, Rhodes, and Zwirnik on non-negative rank. So a non-negative real tensor of any format has non-negative rank at most 2. Well, first of all, it has to have rank 2, that is to say it has to satisfy these cubic equations. And then there's a very simple system of inequalities, disjunctions of inequalities like this. So the entries might satisfy something like x111 times x222 is greater or equal to some other product, and we call that the multiplicative supermodularity, and that's a system of equations and inequalities that characterizes non-negative rank 2. So for rank 2, we have complete information. Maybe, I don't know whether I have it on the slide, so let me give you an example of a matrix so you just can ponder this. So here's an example of a matrix whose non-negative rank exceeds the rank. So let's look at this 4x4 matrix with 0, 1 entries. So it has classical rank 3, right? The vector 1, minus 1, 1, minus 1 is in the kernel, but the non-negative rank is 4. So if you try to factor that as a 4x3 matrix times a 3x4 matrix, you must pick up a negative number along the way. So there's no way to decompose that, what we did in the soccer case, into a sum of 3 independent tables. Yes, question?
Can we decompose it into 4?
Yes. Yes.
If a non-negative rank.
So for example, just break up the different rows. Right? If you zero out all but one, or columns, zero out all but one of the columns, you have a non-negative rank 1 table. Okay, higher rank is much more complicated, and I just want to sort of state one recent theorem that's quite beautiful. So first of all, this was subject of tensor rank, has been studied for quite some time, especially in algebraic complexity theory. So there's one very popular tensor called the matrix multiplication tensor, whose rank people have been very interested in. And Strassen, in this context, over 30 years ago, showed that a 3x3x3 tensor has rank at most 4, if and only if a certain explicit polynomial of degree 9 vanishes. And this is part of the 4x4x4 salmon story. So, you know, to have rank 1, certain quadratic polynomials vanish. To have rank 2, on the previous slide, certain cubic polynomials vanish. But here, to have rank 4, we need equations of degree at least 9. However, there's a beautiful finiteness theorem due to Dreismer and Kotler, published this year, that says the following. Suppose you give me any rank r. We fix a rank r. Then there exists a universal constant d, depending only on your r, such that a tensor of any format whatsoever over an algebraically closed field has rank at most r if and only if certain polynomials of degree d of r at most d of r vanish. So d of 1 is 2. d of 2 is 3. That was the previous slide. d of 4 is at least 9. Okay, so we don't know any bounds. We don't know, there's no good formulas. It's actually a topological argument. You show that a certain space is Noetherian. So using an inconstructive topological argument, we get this result. So I wanted to end the discussion of tensors with the Dreismer-Kotler theorem. So you give me any rank, say 7, then there exists some universal constant, maybe 1,000, such that to characterize tensors of rank at most 7, I need equations of degree at most 1,000. There's no bound. There's no bound known at the moment. It's an inconstructive proof. Okay, new topic. See, the nice thing of having about 3 different topics is you can always reboot. Okay, so new topic, start again. So in polynomial optimization, an important paradigm is the concept of semi-definite programming. So let me tell you about semi-definite programming. It's the problem of minimizing a linear function over a spectrahedron. And what's a spectrahedron? A spectrahedron is the intersection of the cone of positive semi-definite real symmetric matrices with an affine linear space. So positive definite matrices, they form a convex cone. And that positive definite cone, I mean, it's not a polyhedral cone. from far away, it looks like a round, nice ice cream cone. But just like with ice cream, as you get closer, trying to lick the ice cream, you notice tiny ripples in the boundary of this cone. All this, and that's where all the action is. So all the action is in the singularity. So it's not a smooth cone. It's not a polyhedral cone. It's not a smooth cone either. So you cut this cone with the linear space, you get a convex body, and such a convex body we call a spectrahedron, and want to optimize a linear function over this. Now, an important special case is one that you're probably familiar with, namely if your linear space of matrices consists of diagonal matrices only, right? Well, the diagonal matrix is positive definite, only, that's if the entries are positive, right? So in that case, the cone is the orthant. Now, what happens if you cut the orthant with the linear space? You get a convex polyhedron, or polytope if it's bounded. So definition of polytope, it's the slice of the orthant with the linear space, and the computational problem of minimizing a linear function over a convex polyhedron is called linear programming. So linear programming, by definition, is semi-definite programming for diagonal matrices. Or a different way of saying that, semi-definite programming is the non-abelian version of linear programming. Spectrahedra, you should think of as the non-abelian version of convex polyhedra. After all, diagonal matrices multiply in abelian fashion, and general matrices don't. And these are pictures. So here's a picture of a polyhedron, and here's a picture of a spectrahedron, certain convex bodies. So these things are spectrahedra. So here, this is one of my favorite pictures. This was on the title page. So if you try to visualize the 6-dimensional cone of 3 by 3 positive semi-definite matrices. Okay, a 6-dimensional convex cone. Slice it with a 2-dimensional plane. Then you get this convex body. That's a 2-dimensional spectrahedron. The boundary is given by the vanishing of this 3 by 3 determinant restricted to the plane. So that's a cubic curve in the plane. It's an elliptic curve. Now, if you cut instead the 6-dimensional ice cream cone with a 3-dimensional plane, then the intersection will be this 3-dimensional convex body. This is sometimes called the elliptope or the samosa, the kind of thing you eat in an Indian restaurant. So this convex body, this samosa, so for a statistician, these are the 3 by 3 correlation matrices, right? So just to write something algebraic. So if you take all matrices like this, 1, x, y, 1's on the diagonal. So all 3 by 3 matrices that make this positive semi-definite, that's the yellow shape, right? So this means positive semi-definite. So this has 4 singular points. It looks a little bit like a tetrahedron in which you puff a little air. So you take a tetrahedron, you go, and it bulges out a little bit. The edges, the vertices, the 4 vertices and the 6 edges of the tetrahedron, they stay on the boundary. They stay faces, but otherwise it's rounded out a little bit. And here the elephant ears, this is the Zariski closure of the boundary. So out here the cubic surface continues. And now I don't know the audience, maybe there are some algebraic geometers in the audience. So for you, the riddle is which 6 points in the plane do we blow up to get this cubic surface? Now duality, and that's the theme of this slide, is very important in optimization. It's very important in geometry. And on the right side, you have the dual picture. So here in semi-definite programming, you want to optimize a linear functional. So let's pretend we do this like in calculus by looking at when the gradient vanishes. So let's say we want to optimize the linear functional go southeast. So I'm going to say beep whenever there's a critical point. Okay, you ready, Konstantin? Beep, 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 beep. Okay? So I said beep 6 times. So you heard 2 red beeps, 2 black beeps, and 2 complex imaginary beeps you didn't hear. Okay? And then to solve our semi-definite program, we use the one that we picked best. So in classical geometry language, this is a curve of degree 3 and class 6 beeps. In the dual plane, we have a curve of degree 6 and class 3. So dually, the beeping corresponds to stabbing this curve with the line, and we're going to say beep whenever we cross, beep, 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 again 6 times. Okay? Now what's the dual? In red you have the dual body in the sense of convexity. So if you have a convex body, there's a dual convex body, but then the stuff out here, the Zariski closure out here, has a duality down here. So the points on this object correspond to lines that are tangent on the primal curve and vice versa. Here's the dual body in dimension 3. So the dual body to this convex body is this convex body that looks like this. So you take 4 quarters and you make them touch pairwise. So you make a little tetrahedron out of 4 quarters. Well, you didn't quite take the convex hull. You round it out by gluing in this quartic Steiner surface, which is the dual surface to this cubic surface. And then it's this convex body. So this is the convex hull of a Roman surface or Steiner surface. So if you have a device like this gentleman, you can go to the wiki and you can say Roman surface and you see this thing rotating. So I could talk about this picture for the rest of the hour, and it's very tempting to do so. So, well, let's talk about semi-definite programming over this thing. So there are 2 fundamentally different things that could happen, right? Either a linear functional could be optimized as a smooth point. So if we say go north, the optimum would be at a smooth point. So that happens if your linear functional on the dual body is picked here on this curvy Steiner surface. If you pick your linear functional here, then you get optimized at a smooth point, which is a rank 2 matrix in this space of 3 by 3 matrices, right? So on the boundary, this matrix drops in rank to 2. 2 positive eigenvalues, 1 0 eigenvalue. But here at these singular corners, if we want to optimize go east, then we get a rank 1 matrix. If we pick our linear functional from the interior here of this flat circular face, right? This is the set of all linear functionals that get minimized here, and then we get a rank 1 solution. And rank 1 solutions, those are the ones that practitioners want. So if you want to solve a compressed sensing problem or the Netflix prize or something, it's the low rank, the rank 1 solutions the engineers would like to find. Let me say one thing, how I got to semi-definite program. It's by way of the polynomial optimization problem. So suppose f is a polynomial in m variables of even degree 2d. And suppose you knew that this is bounded below and attains a minimum x star, you would like to find that global minimum x star. Okay? That's a hard problem in any sense of the word hard. Now, of course, minimizing a function is equivalent to maximizing the lower bound, right? So I want to find the best lower bound lambda such that f minus lambda is a non-negative polynomial on R to the n. That's hard, so let's do something else instead. Let's replace the condition that f minus lambda is non-negative with the condition that f minus lambda is a sum of squares of polynomials. Now, of course, if you are a sum of squares over the real numbers, then you're non-negative. Right? But maybe we're lucky. Right? Maybe it's the case that every non-negative polynomial is a sum of squares of polynomials. So that's a question that was asked by Minkowski and answered by Hilbert. Unfortunately, it's not quite true. Right? So there are some non-negative polynomials that are not sums of squares, but let's pretend for a moment they were. Then I claim that this is a much easier problem. The second red problem is a semi-definite program. It's one of those beeping problems we saw on the previous slide. Okay? Now, the optimal value of this semi-definite program often agrees with the global minimum, and the optimal point can often be recovered. Why is that? Well, you pass to the dual semi-definite program. If you are lucky, the dual solution will be a black rank 1 matrix. But if you have a rank 1 matrix, right, it factors like this, and this is essentially your solution point x star. Okay? Again, there's a textbook that you can read on these things, the book by Bleckerman, Parillo, and Thomas, called Semi-Definite Optimization and Convex Algebraic Geometry, and I will explain this approach in a very, very simple example on the next slide. Let's look at an example where m is 1 and d is 2. So we have a polynomial of degree 4 in one variable x. And our problem is to find the global minimum of this polynomial. Now suppose you were lucky and you never had to take calculus, or you forgot everything about calculus. Then here's how you approach this problem. So we'll not use calculus. Instead, we will use the approach I just described. We're going to look at f minus lambda, and we ask for the largest lambda such that f minus lambda is a sum of squares. Well, what does that say, being a sum of squares? Well, we represent this quartic as a quadric in quadrics, but the outer quadric is supposed to be positive semi-definite. So in English, we write down a general enough 3 by 3 symmetric matrix. It has the lambda, and it has a free parameter mu. And then we multiply with the row vector of all monomials of at most middle degree, x squared x1, same column vector over there. You multiply this out, you get a scalar, and that's an identity. That's f minus lambda. Okay? So the mu is the most general parameter that you can stick in here so that you get an identity. Okay? So our goal is to maximize lambda such that this matrix is positive semi-definite. Okay? But that's exactly the problem we've seen, right? We're now in the mu y plane, right? This is a spectrahedron we have, this elliptic curve. We want to say go north, right? This is the picture corresponding to this problem. So let's solve it, right? So you take this semi-definite program, you type it into MATLAB or something, and in 0.000001 seconds, the answer comes back. So the optimal value for lambda star is negative 32, mu star is negative 2. So that says the optimal value is negative 32, but we can also recover, in this case, the optimal solution. So how do you do that? So you plug in these parameters here. Now you have a rank 2 positive semi-definite matrix. You Koleski factor that into a 3 by 2 real matrix times its transpose. So you have a positive semi-definite matrix. You can take a square root. That's called Koleski factorization. And then you rewrite the Koleski factorization, right? It's a sum of two squares. So f plus 32 is this square of a quadric plus that square of a quadric. So we found the global minimum together with a proof, with the certificate of optimality. And this approach works for a wide range of optimization problems. It's not snake oil. It does fail in some cases, but it's a very active area of research, and it's sort of the current paradigm of solving polynomial optimization problems involving equations and inequalities over the real numbers. Okay, any questions, either about tensors or about spectrahedra and how they're used? Yes?
So is there some sort of measure or four-dimensional reason why you would expect that the positive polynomials generic, or not generically, but in most cases,
Yeah.
be sums of squares?
So they are not. So there are actually negative results. So there's actually a work, an important work of Blackerman, who showed if you fix the degree, say at 4, look at quartic polynomials, and the number of variables goes up, then in fact the ratio of sum of squares polynomials inside all polynomials goes to 0. So there's some evidence that most non-negative polynomials are not sums of squares, but it depends very much on the measure, how you make your instances. So there's another sort of competing point of view that says that in the kind of sums of squares problems you get from polynomial optimization, from this situation, the verdict is the other way around. But that's an active area of research, and we don't actually know yet. We skip this? Yes.
In this example, why this lower bound is achievable?
Oh, you plug in, right? So,
No, I mean, but we are.
no, not a priori. In one variable, it's a theorem. So in one variable, if you have a polynomial in one variable that's non-negative, that's then it's always a sum of squares. So you never have to do calculus ever again, differential calculus. You can always use this method. But in several variables, no, we don't know. Only after the fact, if we look at the dual optimal, if it's a rank 1 matrix, if it's one of those pointy corners, then you can conclude, but we don't know ahead of time. Otherwise, it's polynomial optimization for one thing is NPR, right? So this is a polynomial time algorithm.
Is this method computationally harder than the calculus method?
No, much, much easier. Yeah, so the calculus method, you have to, so to solve this, you have to actually solve a system of polynomial equations, which is very, very hard. So I should have said that. So semi-definite program, there are several reasons why it's so popular, but one reason is there's a polynomial time algorithm. So in linear programming, there's something called the interior point methods. So they're interior point methods that have a good complexity, and essentially the same algorithms for the same reason work on semi-definite programs. So what works well on polyhedra works just as fine on spectrohedra. Okay. So let me come to the third and last topic. So I think I have 21 more minutes, all right? So I can slow down a little bit. Let's go back to statistics. So one thing that statisticians do, they use statistical models to fit data, to solve inference problems. So you can ask the question, what is a statistical model? Well, you go, for example, to the wiki, the source of all wisdom, and you read that in mathematical terms, a statistical model is frequently thought of as a parametrized set of probability distributions. So p theta is a probability distribution on some state space, and theta ranges over some set of model parameters. So typically, this is some subset of some r to the n. Okay? So this is the definition. Now, let's say theta is a finite dimensional space, maybe a two-dimensional space, and we have distributions. So the state space of these distributions could be continuous, such as in the Gaussian curve, or it could be discrete, such as in the case ACGT. So most of what I say, my examples will be discrete for discrete random variables, but the understanding is that it also applies to some of the continuous situations. But I will mostly talk about discrete things. So here's a cartoon for a statistical model. Now, so think about, this is the space, maybe a representation of the parameter space, and then for each point in this blue parameter space, there's a probability distribution. Okay? Now, when you look at this, so if you look at a statistical model, the way you think about it, that depends on your mathematical upbringing. Okay? So in this audience, so if you happen to be Gunnar Carlson, the first thing you see is a topological space. You look at holes, right? You see how many holes are there, what can you say about the holes, and maybe you think about homology and persistent homology, and that leads you to introduce a subject called topological data analysis, which I think has been presented in this seminar. Now, if you're trained in differential geometry, then maybe what you're most interested in, you're focusing on these smooth points, you might be very interested in the curvature, the local differential geometric structure, right? You might see here a Riemannian structure, a positive definite matrix attached to every point. You might see connections, all that kind of thing. And Amari in Japan saw that, and that led to the field of information geometry. So information geometry is the study of statistical models and their application from the point of view of differential geometry. If you're me, you see an algebraic variety, right? You see the global algebraic geometry. There will be some polynomial, maybe of degree 4, that vanishes on this equation, and maybe using this polynomial, you'll be able to say something, and that leads to algebraic statistics. So what I'm trying to say with this slide is that data are very, very important. Every university is starting a program in data science. And, you know, the statisticians are, of course, key. Statistics, after all, is the science of data analysis. And the computer science tend to be very fast at getting the cake. But I think as a geometer and algebraist or topologist, there's some very, very interesting question. And I think looking at spaces of data and statistical models in this sense, from the points of view of different geometries, should be very, very fruitful for, let's say, data science. Okay, so in the remaining time, I'm going to focus on this perspective. So there's one of these perspectives is that of algebraic geometry, of nonlinear algebra, and that's algebraic statistics. So let's look at two discrete random variables, x and y. So x has m states, and y has n states. Okay? So if you have a joint distribution for these two random variables, you can write this as an m by n matrix of non-negative real numbers whose entries sum to 1. Right? So Pij represents the probability that the first variable is in state I and the second variable is in state j. So for example, x might be the soccer random variable with 3 states, so m is 3, and y might be the hair, little, medium, high, and n is also 3. Now the space of all distributions is a simplex of dimension mn minus 1, and inside that simplex I can look at the manifold mr of matrices of rank exactly r. That is a manifold. Now, let me say one more word. So sometimes you hear lectures about manifold learning. Now a manifold, this would be a manifold if it weren't for those singular points. Okay? But very often in statistics, all the action is at the singular points. So you have to be very careful about using the word manifold and manifold learning. This is these things are generally not a manifold. We're just going to pass to the closure in a minute. So matrices in M1, so those are independent distributions, rank 1 matrices. And this is the pictorial representation. So these things are graphical models. So in graphical modeling, you have a hidden random variable. So there's a hidden random variable z that has r states. R is the rank. So z might be gender, has r states. And then the visible variables x and y have m and n states respectively. So this model represents mixtures of r independent distributions like in the soccer example. So this represents conditional independence. Now, in statistics, there are two classical approaches to inference. So historically, there are two camps. There are the Bayesians, and then there are frequentists. Okay? Nowadays, it's all different. But historically, there are those two camps, and they're looking at the same object, but they're doing different things. So let me try to explain that. Suppose we have a data set, and we're summarizing this in a matrix. So U is a matrix of non-negative integers, and the entry Uij is the number of samples with x and state I, and that's, for example, that's my soccer hair matrix, right? So that's a non-negative integers, and the total sum of the entries is a sample size. Okay? So then I'm going to look at the likelihood function. This is simply the corresponding monomial function. So Pij is the unknown probability of seeing something of form ij, and then I multiply them. These are independently drawn samples. There's a multinomial coefficient out here, but except for this multinomial coefficient, this likelihood is the probability of seeing my particular table given that the PIGs are the probabilities and given the sample size. Okay? So you ask 1,000 people in the street for their hair length and for their soccer watching. There are lots and lots of possible tables that you could see. Right? Each of these tables has a probability. It is a monomial in the PIJs, and that is the likelihood function. So now if you are a frequentist, your goal is one of differential calculus, namely to maximize the likelihood function. We like to find, within the model constraints, we like to find those probabilities, Pij, that maximize the probability of seeing the data that we in fact did see. That's likelihood, maximum likelihood. In Bayesian statistics, people do something else. In Bayesian statistics, people integrate this function. So there you have a prior belief on the model. So there's a distribution on the model, and you integrate this likelihood function against the measure. And you make statements about that integral. So to first order, Bayesian statistics is about integral calculus, and frequentist approach is about differential calculus. And algebraic statistics harmoniously works with both, but here I'm going to focus on the likelihood inference problem. So we want to maximize the likelihood function subject to P being of rank R. Now typically there's a unique solution called P hat, and will be a rank R matrix, and we call that the MLE, or the maximum likelihood estimate for the data. So just to make this very concrete, we have the following optimization problem in the soccer case. So we have unknown probabilities, P11, P22. We have known data, so these U's are known positive integers, and want to maximize this function subject to two constraints. So the determinant vanishes, that's the rank 2, and then it's supposed to be a probability distribution. Okay? So we would like to find non-negative real solutions. Now always in applied algebraic geometry, we're typically given a problem over the real numbers, maybe the non-negative real numbers. Those problems are very hard. So we make the problem easier in 3 steps. Step 1, ignore the inequalities. Step 2, replace the real numbers by the complex numbers. Now the problem is much easier, right? So complex numbers much easier than real numbers. And third step, replace affine space by projective space. Now it's even easier, right? Any 2 circles in the plane meet in 4 points, right? So now that we made the problem so easy that it's in complex projective space, it's so easy that even algebraic geometers might be able to say something about it. So that's what we're going to do. We're going to look at complex critical points in projective space. So here again, what would you type into Sage or Maple, right? So we would like to type the determinant as 0, and then the sum of the entries is 1. And then we use Lagrange multipliers, right? So Lagrange multipliers says we have this determinantal variety of rank R matrices, and we would like to find a point at which the gradient of the objective function is that hyperplane contains the tangent space. So the gradient of the objective function should be orthogonal to the point. That's Lagrange multipliers, and that translates algebraically into this condition. So if we form a 3×9 matrix, the first row is the flattened, let's say, or vectorized version of the data. Here we have the unknowns. And then finally we have this cubic entry, so Pij times the cofactor in the matrix, the derivative of the determinant. So now you type this into your favorite computer algebra system, and you find that there are 10 complex solutions. So there are 10 complex critical points. In general, we study the ML degree, the maximum likelihood degree of a statistical model or a projective variety is the number of complex critical points for generic data. So if I have a random data set U, then there's a fixed number of critical points. Again, so what you usually do, you replace this with the logarithm, right? So it becomes Uij times log Pij. And if you take the derivative of the logarithm, you get 1 over x. So that's an algebraic problem. So it's sometimes called logarithmic geometry, right? So we take the logarithm, and the derivative of the logarithm is 1 over x. So here's a theorem that tabulates the known values of the ML degree for the rank varieties VR. So VR is the complex projective variety of matrices of rank at most R. Well, first of all, so this is the matrix sizes, 3×3, 5×5, and this is the rank. So here for rank 1, it's very, very simple. So there what you do is you want to find the best, in the likelihood sense, rank 1 approximation to your data table. We teach this to freshman biologists at Berkeley. So here's what you do. You have your data table. You form the row sums. You make the vector of the row sums. Then you take the column sums. You take the vector of the column sums. You scale them, both of them, by the sample size. And then you multiply like this. And then you get the rank 1 matrix. And that's the optimal solution. That's the unique critical point. And that's for rank 1. For top rank, right, if you have a 4×5 matrix to find the best, rank 4 approximation, well, you just give that, you divide by the sample size. Right? But here's something interesting. So here's our number 10, right? So we saw that for 3 by 3 matrices in rank 2, the ML degree is 10, and so on, you know. Maybe for 4 by 5 matrices of rank 3, the ML degree is 843. Now, when we did this study and we calculated these numbers in Bertini using numerical algebraic geometry software, so maybe the word hasn't gotten around yet. So in computational algebraic geometry, for the last 25 years, the paradigm had been symbolic computing. So Gröbner-based engines such as Macaulay, Singular, had been the standard in computing algebraic geometry. But in the last 5 years, it's been recognized that using purely numerical methods, you can go further. And many of the things you can do with Macaulay and so on, you can do with Bertini. So this was all done with Bertini. But we were very surprised to find that there's a symmetry down the columns. So we didn't expect that. And this was explained recently in a work by Jose Rodriguez, but more general. But we were at first quite surprised that there's a symmetry, that the rank 2 critical points are in bijection with the rank 4 critical points. Now, since there's a semester here on the topology of algebraic varieties, let me tie this in. So there's very nice work of Jun He that says the following. Suppose for a moment these varieties were smooth, which they're not, but suppose they were, then this is just the topological Euler characteristic. So it turns out if these varieties were smooth, these numbers, that would be just the Euler characteristic of this complex manifold. Now these things are not smooth, so this is not quite the Euler characteristic, but there's a close relation to the CSM classes, so Chern, Schwarz, McPherson classes. We don't completely understand this yet, but there's some very nice connection. And June, I think, is here for a long time, and he can tell you everything about that. Let's do one example. So there's a similar story for symmetric matrices. So suppose we have a symmetric, we have this data matrix, and we want to find, so this is 2 identically distributed ternary random variables. And we like to find the best rank 2 in the likelihood sense. So for this data table, the ML degree is 6. There are 6 complex critical points. I wrote down the coordinates and floating point approximation. We want to maximize the log likelihood. The log of a number between 0 and 1 is negative. If you want to maximize a negative number, you find the one of smallest absolute value. Okay? So this is the global winner. But then, in this case, all 6 complex critical points are real, and they're all in the simplex. They all have positive coordinates. And the first 3 points are local maxima, and the last 3 points are local minima. And I like this example because there's a very beautiful symmetry that lets you write these numbers in radicals. So you're finding you're having a system of equations, and there are 6 solutions. So if you believe in Galois theory, you would be led to believe that this cannot be done in radicals. So you have to solve an equation of degree 6. But there's some very nice symmetry that drops the Galois group down to S4. Let me close with a few words about what statisticians actually do. So we have this nice theory of maximum likelihood degree, but unfortunately that's far from what practitioners actually do. And for one reason, what do statisticians actually do? They use local hill climbing methods, in particular the EM algorithm, the expectation maximization algorithm, to maximize the likelihood function in these kind of models. The other thing that they do is they work in the space of parameters, theta, rather than in the space of distributions. But there are a lot of mathematical issues. There's non-identifiability, there's singularities, there are many local maxima, even in the baby example that we had on the previous slide. And the M algorithm has many, many other fixed points. And another issue is the true model that they're interested in is not low-rank matrices. They're not interested in probability matrices of low rank. They are interested in probability matrix of low non-negative rank. Right? So if you want to approximate the soccer table, You want a low-rank matrix of low non-negative rank. And that's a whole different story. So there's a paper that's coming out in the Annals of Statistics called Fixed Points of the EM Algorithm and Non-Negative Rank Boundaries that studies these issues in considerable detail. Okay, time is up. So I was trying to give a sort of a tour of 3 themes in applied algebraic geometry: tensors, multilinear algebra, polynomial optimization, in particular semi-definite programming, and finally the brief introduction to a likelihood inference from the perspective of algebraic statistics. I am not advocating that Grobner-Bayesian or Bertini be used on large-scale applied problems. That would be ridiculous. Of course, linear algebra is and will always continue to be the foundation of scientific computing. Large-scale problems, we will need structured linear algebra methods. What I'm advocating, though, is do not throw away nonlinearity too early. Right? Do not linearize right away. Try to maintain inherent nonlinearities and structures that come from the nonlinearities as long as possible before passing to a linearization, before passing it off to your friends in numerical linear algebra. Okay, that's about it. That's a spectrahedron. That convex body is not a spectrahedron. And that's, of course, the Como surface with the 16 two torsion points on an abelian surface. Thanks for your attention.